Dirac was one of the inventors of QED, like he wrote down the first kind of. He went to his grave not liking renormalization. He thought that renormalization of all these, like subtracting out these infinities and stuff, is a bit of a cheating. And he always wanted to, have a better theory of QED, like something where you wouldn't have to do this subtraction of infinities. It was kind of amusing that somebody who kind of invented the subject then became very aloof from how it developed later, in QED especially. Einstein just used Riemannian geometry, right? Riemannian geometry already existed. But QFT is one topic where, rigorous mathematics still not exist, except in certain topological, maybe QFTs. I'm not saying all the scientists are honest, and maybe some scientists, do steal some research grants, buy an expensive ticket, later cancel it. There is some amount of pilferage that is happening. It is so hard to discourage that mentality that, as a PhD student especially, you are a colleague, you are supposed to contribute to the research at an equal level. Like, I might not know things, I will learn things from you as a PhD student. So having that, self respect, and having that importance to yourself, that yes, कि भाई मुझे भी कुछ आता है, right? Like, I am a worthy human that knows something and can contribute to these projects.
So hello everyone and welcome to the podcast. Today's guests work on some of the deepest questions in theoretical physics. In this conversation, we explore the topics ranging from black hole information paradox to string theory, quantum gravity, to even AI in scientific discovery. We also talked about research culture, education, funding, and the future of science in India. What particularly enjoyed was the sheer breadth of our discussion. Beyond the technical aspects of physics, we explored the questions about curiosity, learning, scientific institutions, academic culture, and what it takes for science to thrive in a society. And I am really excited for you to hear this conversation and the ideas that emerge from it. Please join me in welcoming our guest today.
Raghu, I want to start completely from scratch. So I'm going to ask you some questions that might sound basic, but I genuinely believe the answers are surprising, and I want to make sure I actually understand what I'm talking about before we go anywhere deeper. So, before we can talk about information being destroyed or preserved, I need to understand what the word information actually means in the context.
Yeah, so you can be very precise. Information in this context, depends on the what kind of problem you are studying. So let's say you are studying classical mechanics of, many particle system. Then the information is basically, how many variables are required to specify the state of the system completely. So for example, if you have 10 particles moving in 3-dimensional space, you can completely specify their configuration using, 10 positions. Each position is a 3-dimensional vector, and 10 momenta, which are 3-dimensional vector. So this collection of numbers of the particle's position and momenta at some given time becomes the information that is carried by these particles. Okay. So similarly, if you're doing quantum mechanics, in quantum mechanics, the relevant equation is the Schrodinger equation. And there, the relevant thing that specifies the state of the system is the wave function. So if you completely know the wave function of a particle, that is the information content of the physical system at that time. So basically, information just means whatever you need to know to specify the state of the system completely at some time.
So, like
So,
in context of black hole, we give an example of book falling into a black hole.
no, so you can think about it first just purely classically. One doesn't need to talk about black holes or books or anything. Just, imagine some complicated a system consisting of many particles, like just undergoing natural evolution according to its equations of motion, like just in classical mechanics, right? Now, the point is, even initially, if you started the system in a very simple state, which means that you can very easily specify the position. Let's say all particles are uniformly distributed in the room, and they all are moving with, half of the particles are moving to the left, half are moving to the right. So this is something which is very simple to specify, right? And but as the time goes on, the evolution will take the system to a much more complicated state. Like the positions will evolve according to the equations of motion, and momenta will also evolve according to the equation of motion. So after, let's say, a long amount of time, the positions and velocities will be some very different numbers from what you started, right? Now, if the pattern of those numbers is not very simple, then it's very hard to keep track of all the data that is there in the system, right? You might just forget about the position of every single particle and try to sort of describe it in terms of some averages, just because the underlying exact description is very complicated. So, what people mean when people say information is preserved is that in almost every physical system we know, the state of the system at some early time can be recovered from the state of the system at a late time, right? So that is what it would mean for the information to be conserved. That means if I took the system from time 0 to time 10, and if all the information is still there, I should be able to come back and figure out what the state of the system was at an earlier time. So
So
that's
why do
all
you
it
worry
means.
about, especially about black holes? Like, my phones radiates heat, my stars radiates light. Both
Yeah.
of this process looks irreversible, but I cannot look at the heat coming out of my phone and reconstruct what app I was running. So why?
No, you can. In principle, the
Yeah,
statement
in
is in
principle you can.
principle you
Yes, in
can.
principle. But like, why that also is not information paradox? Like stars, every star is radiating heat.
Yeah, the paradox comes because in the black hole context, there was some more reason to believe that this process of emitting radiation is irreversible, right? If you had an app running on your phone and you like completely shredded your phone to pieces, you can imagine like if there was a very super smart detective who could collect all the pieces of your phone and everything that came out of it, and he in principle should be able to assemble your phone back, right? There is nothing in the laws of classical mechanics that prevents that from happening. Okay, so that therefore there is no information paradox. But in the black hole context, Hawking seemingly did a complete calculation which seemed complete at the time and showed that basically no matter what the initial state of the black hole, the final state seems to be the same. So that means that from that final state, if I go back, right, I cannot recover many different states that I started with, that I could have started with. So it's like the time evolution should be a one-to-one function, not a many-to-one function, right? But Hawking kind of showed by his calculation, which now we understand was subtly wrong. But at the time, it seemed completely plausible that, many different initial states, when you pass them through the time evolution through the black hole, end up as the same final state. So basically, the contradiction, simply speaking, is whether the time evolution map is one to one or many to one. Okay, and if it is many to one, then you would say there's an information paradox.
So what was he actually working on when he wrote that 1974 paper?
Yeah, so he was trying to, analyze the process by which black holes emit radiation and so on. And, he wanted to see where in the equations that describe a black hole, could something reversible enter? Like, where is the scope? And basically, he couldn't find it. Like, so, if you like literally do the calculation, you find that it's the time evolution is a many to one map. So he was trying to study based on info, like, so okay, so coming back to just thermodynamics, 19th century physics by Boltzmann and Maxwell and these people. There is also a puzzle, like why in real life, as you're saying, if you're running an app on your phone and I come and burn your phone, you know it in principle it seems like, even I mean in practice it seems like you cannot recover the information back. But it's not that it is impossible, it is just extremely hard, right? But in principle it is possible. So one should start distinguishing questions of hard versus impossible. Hard could be very impossibly hard for any amount of technology that we have.
So what I
So
think that
mm, yeah.
Hawking was not wrong. So he was answering a different kind of question than he thought he answered the first. So
No. Hawking, in fact, was his calculation we now understand was incomplete, basically. Like he had done the calculation and it at the time, around the tools and the theories available at the time, it seemed a complete calculation. But now we understand that there are pieces of that calculation that were just not taken into account. So we are studying the same question.
What happened after Hawking? Like, who were the
Yeah.
people who taken that problem and started
Yeah.
to work on that?
Yeah. So I think there is a big history of, some people actually believing that information is destroyed and trying to make a theory out of that, and and so on and so forth. But basically, one of the biggest hints came from string theory, that something is not correct with Hawking's argument, because one thing is that string theory gave a microscopic explanation for the entropy of the black hole. So, black holes
So
don't just have a temperature, they
it
have an
is
entropy.
related to Banks-Stein work, Jacob
Yeah,
Banks-Stein work.
right. So Bekenstein gave some general arguments that the entropy of a black hole should be proportional to its area. So they are some thermodynamic kind of arguments. But since the 19th century, we have understood that if you have a microscopic model of your many particle system, then entropy is nothing but the log of the number of states available to that system. So, one needs to connect these two ideas. On the one hand, Bekenstein is saying entropy equals area. And on the other hand, if you expect that black holes are just normal objects, then that entropy should be coming from log of some number of states. You can ask, where is that number of states, or what are those states? And in classical GR, there is no option. Like, basically, there are these no-hair theorems that tell you that equilibrium black holes are essentially unique. So in classical general relativity, there is no scope of having many, many underlying different states of the black hole, which will lead to this log n amount of entropy, right? So string theory provided that for certain special classes of black holes. Okay, so then people started believing that now that has a temperature, it has an entropy which is explained by some underlying, basically some part system made of particles and strings and whatever. So it doesn't look that different. So then people really started believing, no, something must be wrong with Hawking's argument. Or not wrong, but something is missing. What he did was correct, but there is some other piece that has not been taken into account. So then I think the sharpest version of this puzzle that we now understand was posed by Juan Maldacena in a paper from the early 2000s called Eternal Black Holes in Anti-de Sitter Space. So in 95, Strominger, Waffa, and Ashok Sen developed this theory of counting entropy of black holes. And that program led to the discovery of this so-called ADS-CFT and holography, which led to a precise definition of a theory of quantum gravity in space, certain kinds of spacetimes, not the ones we live in, but so-called negatively curved spacetimes. And in that setup, uh, it is completely clear that the the model with gravity has an alternative equivalent description in terms of a model without gravity. So, then people really started believing that black holes are not really special. And then what Juan did in this paper from early 2000s, he proposed a sharp diagnostic, which is called a thermal 2-point function, which essentially measures how much noise is injected by coupling a system to a reservoir at non-zero temperature. And he said that, and he again posed it as a puzzle. He said that if you do a naive calculation like Hawking did for this quantity, then you will find a certain type of answer that this thermal 2-point function as a function of time will continue decaying in time to zero. But the expectation from a normal system is that it should not decay continuous to zero. There should be some kind of erratic fluctuations around the exponentially decaying curve. And then he posed it as a challenge that how can we describe these erratic pieces at late times? And that is what was not fully understood, but partially understood in a series of papers starting around the year 2018. And the new ingredient was that when you set up the calculation of this thermal 2-point function, there are certain new contributions that Juan had not thought about, and Juan had not taken, just like Hawking in his calculation had not taken into account some other contributions to this particular quantity that you're trying to compute.
The problem initiated in 1940s, 74, 50 years, best of the mind in the world working on it, and it's still not fully understand. So recently something happened in mathematics. OpenAI models produce a counter example of unit distance conjecture, a problem open since 1946. But what made it interesting was not just how it's solved. Mathematicians said that human community has anchored onto believe that conjecture was probably true, and the models didn't think in that way. AI didn't thought that it was a you know something to prove. AI didn't have that prior. It was
Mm-hmm.
willing to try to building a counter example when
Mm-hmm.
we stopped trying. So
Mm-hmm.
my question is, in your field, are there places where the community might have the same kind of anchor, kind of belief so widely shared that people have stopped seriously questioning it, and where something that doesn't share the pair might find something humans are systematically missing.
Yeah. Yeah. I think that this black hole information kind of questions are not right now the right target for AI. Because the thing with mathematics, number theory, and these discrete combinatorics kind of problems is that they're extremely well defined. And the solution that you produce is also checkable, right? So there's a tight kind of rope that the AI model has to walk. Like, yes, it is true that humans had not tried that approach and they were kind of wary of trying that approach. But the point is that the problem itself was extremely well defined. And the methods that you're using might be complicated and hard, but they were well defined, right? Whereas the trouble with something like this black hole information problem or quantum gravity is that the concepts themselves are still evolving. So the conceptual foundations have not been laid yet. So in that kind of scenario, it's very difficult for AI to, operate. So that is a very different thing. Now, there are other areas of physics which might benefit from AI. I'm not saying that. But this specific area of quantum gravity doesn't seem like immediately the right target.
So my question was not like AI might help with calculation. So
Mhm.
I mean, what is the actual belief in quantum gravity that might be wrong in the way Eurod's conjecture was wrong?
Oh, is there something that we truly believe that might be wrong? And yeah, that's an interesting question. I wish I had thought of this before, but like the thing that people are skeptical about or people should check in more detail. Um, yeah, people actually maybe not in quantum gravity, but in hard questions in quantum field theory, for example. I'm thinking on the top of my head, so thinking out loud might lead to the opposite conclusion. But in various non-supersymmetric systems, now people have kind of you know propose some dualities like strong weak coupling dualities in completely non-supersymmetric systems, and people believe sometimes that these dualities are true, but then maybe later they could be proven wrong. So maybe that is one area where one could try, but again that is an area where the tools and techniques are not very standard. Like essentially every new paper that somebody writes, like they are inventing like a new trick to kind of solve that problem. And it's not like some trick has been sitting there and that humans have just not like been persistent enough to try it. So again, I would think that that kind of problem is maybe out of reach for the current AI models. But there are definitely, conjectures that people make about dualities and then they turn out to be slightly wrong or maybe completely wrong. So, for example, like, yeah, people sometimes believe that a certain lattice model, in the infrared will flow to some fixed point CFT. But sometimes it's not like a real CFT, it's like a complex CFT with a true CFT nearby in the complex plane or something like that. So there are questions like that. Yeah, but in like sort of high energy physics, um, yeah, I don't know. Yeah, I don't know. Yeah, it's a good question. Maybe one should think about it more.
So yeah. So when you say physicists are inventing blueprints, what exactly is being invented? So like new mathematics or new way
Yeah,
of looking at.
sometimes
Yeah.
like new mathematics. Yeah, sometimes that happens. Uh, but many times it is just that, that particular trick is very suited to the particular problem you are studying. like, and it was just not thought of before or something like that. Um, yeah, I mean, it is hard to think of an example. Yeah. I don't know. For example, this whole story about D brains, basically the math was kind of invented along the way, right? Like, and uh, the D brain physics, holography, um, yeah, in string theory. Yeah, sometimes, the calculations you do just use the normal tricks and the calculation was just hard so that nobody had done it. Or there were subtleties involving divergences. So often it happens that, in physics, the answers are infinite. Like in QFT, you have this renormalization problems and so on. And in string theory, also those problems are there. And, computers, if they're just doing numerics, have a very hard time understanding infinities, right? So that is something where human kind of ingenuity has to come in and say, for example, in the whole story of renormalization, it is still very confusing, right? But I think maybe it would have been interesting to see if computers could have come up with the idea of renormalization, like AI, because you naively find something that is infinite, but you don't give up. Like, you still try to make sense. Like, okay, what is the thing that is being physically measured? And this is how we should really model it rather than this naive ultraviolet divergence you are getting, right? So, for example, that is one of the subtlest points about quantum field theory and how people kind of came to believe in it after World War II, after the work of Schwinger, Dyson, and Tomonaga. So that is the kind of thing I mean, that renormalization was invented by physicists. Like, mathematicians would have just said this problem is really not defined. Like, what are you doing? There are all these infinities in the calculation, so just like go home. Like, like this just ill
Yes,
defined.
even if you like the history of physics, so most of the mathematics was invented by physicists.
Yeah, sometimes that is true, or sometimes it's reinvented. Like, uh, or sometimes yeah, I mean, Newton had to invent calculus, and maybe Maxwell had to invent some things. But for example, Einstein just used Riemannian geometry, right? Riemannian geometry already existed. I think in quantum mechanics, that is more true. Like, this whole theory of functional analysis and infinite dimensional Hilbert spaces kind of got an impetus from the discovery of quantum mechanics. Like, those theories were not very far apart. But QFT is one topic where, rigorous mathematics still not exist, except in certain topological, maybe QFTs or something.
So it sounds like you are saying that there is a lot of theoretical physics. It's not about solving equation. It's about solving which equation. Like it's
Yeah, it's all.
figuring out which equation deserve to be solved in the first place.
I think that is true in most subjects. So that is like, a question of taste, for example, in mathematical physics,
Yeah.
that which problems are worth pursuing. But that is true, I think, in many disciplines, especially disciplines that are sort of not directly relevant to societal problems, because there you have sort of pressure, like, okay, if you have to help the climate, then that is like your goal. Whereas in something like math or mathematical physics or string theory, it it becomes a question of taste and partly, how and depth. So depth, how do you measure the depth of a certain problem? One way to measure it is that if you prove a theorem, how many other branches of math does it touch? Like, how many downstream effects does it have? Or whether the tool or trick that was invented, is it used in other places, for example? So that can gauge depth of a certain problem. But that is true. Like, you have to sometimes invent the equation, invent the logic. Like, for example, non-abelian gauge theory also, right? Like Yang-Mills theory, like the action and the math of it was basically invented by physicists.
So you how you decide something is needed to be solved. How you decide this problem need to be worked on.
Yeah, so that is a very individual thing, right? At some level. Like, so, people have their own motivations based on maybe where they grew up, what kind of books they read, what kind of people they interacted with, what kind of universities they went to. So all that like plays a role. But I think that is why you need a community of a substantial critical mass number of people, so that, overall collective progress can happen. And unlike one person might go off on a tangent doing something which they might have fun, but, might not be that important after the dust is settled. So as an individual practitioner, doing things, your motivations are one thing. And as a community, attacking a suite of problems is also important, so that humanity as a whole kind of develops a depth of understanding that no single person can.
If you have asked till now, I think you will enjoy the next part even more. So far, we have talked about black holes, quantum gravity, the information paradox, and some of the deepest question in physics. But now the conversation shifts to something much more closer to our everyday life, like how science is actually done. We talked about research funding, academic culture, scientific institutions, education, and the challenges researchers face in India. Now, some people might think these questions are less exciting than black holes. Personally, I don't think so because every scientific discovery comes from people, and people don't work in isolation. They work in inside universities, laboratories, institutions, and cultures. If we want great science, we also have to talk about such conditions under under which science is done. For example, why are some countries able to build world class laboratories, and why do some places attract talented researchers while others struggle to retain them? These questions might not sound as glamorous as black hole, but they affect the future of science. And I think these discussions are important because before improving anything, we first have to understand it. Like we need to understand what's the problem, then we can solve the problem. If there are obstacles in the system, we should be able to talk about them honestly, right? And if there are things that are working well, we should understand those too and learn from them. And in this part of the conversation, Raghu shares his perspective on many of these questions, from research culture and bureaucracy to curiosity, education, and what it takes to build a stronger scientific ecosystem. Before we continue, if you enjoy this long form conversation with scientists and researchers, do consider subscribing. You can also find me on Instagram, Facebook, and Twitter, where I share thoughts from this conversation and things which I'm learning occasionally, and there are some of the behind the scene moments from this journey. Now let's get back to the conversation. Okay, so we can talk about maybe Indian science. In India, we have produced lots of great physicists, theoretical physicists, and mathematicians. If you look back in the history, we have Rai Chaudhary, we have C.V. Visvesara, other like Harish Chandra. But when it comes to experimental, like building experimental, we are really behind. There is a clearly intellectual talent, but we are so much behind in producing capable of contributing to building experiments. So if society can produce people capable of contributing to quantum gravity and string theory, why can't it produce scientific infrastructure at the same level? So what is the
I
bottleneck
think,
in Indian science?
yeah, I think one thing is just a question of money. Like, if you look at how expensive these laboratories are, right? And you need to cultivate a system that is deep, like that goes down to the school level in at least all the major cities, that the laboratories should be well equipped. The teachers should have the knowledge to do the practical, fun experiments and to teach science by doing things. Like, I went to a very good school, like a kind of a rich school in Chandigarh, like where, many of the like whatever IPS, IAS officer kids were coming into this school. It was like a St. Stephen school in Chandigarh. But even there, the laboratory experience was almost zero. Like, you just sat in class because there are 60 students in each class and there are like 5 sections in each class. So they just didn't have the bandwidth or the inclination to, expose us to doing things by hand. And the same thing happens at homes. Like, many homes in India like are poor, like and they don't have the resources to have some engineering based toys, like to have fun just building, tinkering with stuff. So that partly is that depth of culture of fooling around with things, getting your hands dirty, messing around, that is absent, which leads to a lack of curiosity about how things work, to make things different. Like, in the US, for example, there was a big culture of fooling around with electronics. Like, you would get some circuit, make some circuit, get some mechanical device.
The culture of garage in US.
Yeah, garage, for example, and that is partly there because those things are available, partly because those things are valued in society, and partly because people have the resources to, have a garage in the first place. And parents have the money to buy a few extra things for the kids. Hey, just play around with this. here is some money, here is some space, go do what you want. So based on that, I feel that compared to that, doing mathematics or theoretical physics is very simple, because you just need to get a book, and you just need to operate with your brain. You don't need a garage, you just need a desk. And back in the day, you didn't even need a computer, you just need a copy pen, maybe a teacher. If you don't have a teacher, that's also fine, as long as you have access to a good book. You can teach yourself calculus, like you can teach yourself classical mechanics, electrodynamics. And that is the mainly the experience of many kids who want to do well in school, is they do well sitting on their desk, theoretical mathematics, etc etc. So that is the reason. The other thing, of course, is that building a LIGO or building a like particle accelerator, etc., takes a lot of money. And I am not very familiar with the level of investment in those kinds of things in India, but I do think that things are changing quite fast now. This ANRF, this Anusandhan National Research Foundation, is there. It is funding a lot of projects in experiments. In biology, this center NCBS in Bangalore is very good. You're right, like these are still individual examples of brilliance, rather than sort of a national level impetus towards this kind of discovery. But it is true that, I mean, things are happening. There are some radio astronomy telescopes. The LIGO India is now starting to being built. So I think things will happen in the future. And as people, especially in the metro cities, get more money, they get more exposure, like their parents get more exposure about the importance of open-ended explorations, letting kids play with their hands and not just making them sit with books all day long. I think the culture will change. It will take time, but there needs to be like a serious, investment from society and government into building labs, right? Like building libraries is one thing. So that we also don't have as many as we should. But having kind of science labs that are good at the school level in government schools, having teachers that can convey the joy of doing experimental physics or experimental chemistry, whatever. I think unless that comes, you will not get people who are very from the grassroots kind of excited about it. Uh, so that's the difference between experimental science and uh, you know theoretical science. But one should note, although that the there are some famous Indian scientists before the independence era, like C.V. Raman and J.C. Bose, who were experimentalists, right? And they did their experiments in India. But so somehow it's also an interesting question to ask now that I think about it. Where did that kind of get lost? Right? If C.V. Raman could get a Nobel Prize working in experimental physics at that time, wouldn't that have been sustained? Like, or maybe he was just an individual brilliant scientist and couldn't kind of develop an ecosystem, or there wasn't like a societal level push, because these people were also a little bit elite. Like C.V. Raman at least was from an elite family, and if you have those kind of singular exceptions, it's hard to kind of make a culture in a society around it. But maybe it's an interesting question for some historian to pursue about these things.
So it's not just problem of money; it's also problem of culture.
I think it's both, definitely both. Yeah.
Yeah. Also, political incentives.
Yeah, I think partly, you know, at the national level, the political incentives. I mean, now the ANRF is there. Uh, we definitely don't spend enough money on R&D budget, like the national government, as for example, as a percentage of the GDP compared to China, for example. So that can definitely increase. Um, but what I'm talking about is not that. Like, even if you do that at the national level and so on, there needs to be a bit more grassroots excitement about it. Like, I'm talking about every single government school in a mohalla, like, having a lab, or, every sort of reasonably sized community appreciating what experimental science is about. Um, and that takes much more effort, not just at the level of the national government, but state governments, city
Exactly.
governments. Yeah. Yeah.
You know,
So,
I studied in a school in Uttar Pradesh, and that was a Hindi medium school. And
mhm.
till 12th, we don't have even computers
Yeah.
to work with. So it's a big problem. And
Exactly. So that is the kind of thing I'm talking about. Like if and it was the same for me. Like until I got to 10th class, I didn't know how to use the internet. I had seen a computer. I could open a Word document, but I didn't know what a internet was until 11th class, or what email was. So even in a city like Chandigarh, going to these schools, and you are right that, in Hindi medium schools in Uttar Pradesh, Bihar, like maybe even more remote areas, like these things just don't exist. People just don't even know about, these basic
they
things.
actually don't know about it.
Yeah.
Because I had some parental support, so I got to know about mobile phone and internet. But there is school in I was in private school, and in private school computers was not there, and
Yeah.
so forget about government schools.
Exactly. Exactly. So that is the kind of, and it has to be on multiple axes, the efforts. It's not just that you get money, you get a computer in the school, and that'll be it. Because there are many schools that have computer labs, but they like lock them up. They're like kharab ho jayega computer, or they don't let the students play with it. So the culture of tinkering around, and not just clicking on the Microsoft Windows start button, opening Word doc and typing some line, and then closing it, saving it, making it bold, italics, whatever the computer lab we used to do. But letting kids explore things, let them be in the lab, let them break things, have the budget bandwidth to buy a new flask or a new computer or whatever if it breaks. That is the kind of cultural mindset that needs to change at the grassroots level. And that same culture actually, then the kids bring to universities, and that actually is a problem. That I was listening to the some clips from, I think, a previous podcast by Shiraz Minwala, and he had put his finger on a very particular problem that I see even in the theoretical physics students, in India.
So he mentioned that even in students of string theory, they don't know about other parts of physics like condensed matter physics.
Yeah, so the breadth, so people kind of get pigeonholed into thinking about their PhD problem, and not have this thing, oh, I want to just learn this thing because I'm curious. It may not be for any specific purpose towards my PhD, like this is not the project I'm working on, but getting that intellectual depth, that comes from this culture of just being able to explore things, or wanting to explore things, being hungry to explore things, being kind of having that almost greed कि भाई मुझे ये सीखना है, like मुझे ये जानना है, मुझे इसकी एक, almost like a hunger, like a thing that, ambition, that I want to learn this. I just mean curiosity, curiosity, like curiosity for no particular perceived outcome, like, yeah, or even, reading literature. Let's say the problem you are working on, maybe you need to study 3 papers, and then you can do the calculation. At least every particular topic within theoretical physics will have 30 important papers, right? At least one should make an attempt to read those 30 papers, even though they might not, contribute towards your specific project, like things like that, like I'm talking about even. So, and that cultural mindset like needs to change. Like another thing is that, forget about TIF or ICTS, we discourage students to call sir, but when people come having done undergrad from even Delhi University, let's say St. Stephen's College or something, it is so hard to you know discourage that mentality that, as a PhD student especially, you are a colleague, you are supposed to contribute to the research at an equal level. Like I might not know things, I will learn things from you as a PhD student. So having that, self respect, and having that importance to yourself, that yes, कि भाई मुझे भी कुछ आता है, right? Like I am a worthy human that knows something and can contribute to these projects. Like that feeling of self confidence and self respect also needs to be inculcated, and that is not disconnected from the curiosity thing. Because when you are in 7th, 8th, 9th, and you ask a tough question to the teacher, many times the teachers get offended and they scold you कि ये कैसा सवाल पूछ लिया, आप बस चुप करके सुनो, कॉपी में लिखो, और एग्जाम में वैसा ही सेम लिख के रट्टा मार के लिख के आ जाओ, राइट? So that is the kind of culture that gets ingrained, and it's very hard to beat. Like unless you beat that, you're not going to, get these blue skies research, ceiling breaking research coming out at scale. There will be individual, brilliants like Ashok Sen, Shiraz Minwala, Rajesh Gopakumar, like all these people. But at scale, it will not happen unless every person thinks that they are worth something important, like, that they have something to bring to the table which is valuable, and that they need to be respected and treated as an equal.
How you build
That
this
is,
culture, like, because it's not something only problem of money.
yeah, that is why I'm focusing on both things, investment as important, but changing that mindset, which is a kind of almost an educational thing in the positive sense, is also very important. Like opening your mind to saying that, like old people are not always right, like young person can also be right. Like, we have this culture of badon ki respect karo. Yes, badon ki respect karo, but that doesn't mean they're always correct.
Respect is not about questioning. Questioning is
Yeah.
different thing.
Yeah, we respect every human being. I respect you. I respect people younger than me. I respect people older than me. But that doesn't mean that you be ha milaye jao sabki, right? Like that is not the culture that a teacher should be inculcating in the classroom. So I think that is a big difference between the US culture and the Indian culture, and why, the volume of good output is so much more in the West is because of breaking of this kind of shackle of thinking, of this almost kind of subservient mentality or colonial mentality that other people are somehow better than us or something like that. Like that is being broken. It's broken by many people, and we have, as you said, world class theoretical physics research coming out of India, mathematics research. So there are people who break it, but we are not talking about isolated pockets and individuals, like 100 individuals. We are 1.4 billion people. We should have millions and tens of millions of people, contributing good ideas to science.
Because some theoretical physics something you can do alone, and it's
Yeah,
some people collaboration. But
yeah.
experimental, you need
And it's
whole
the same
society to.
problem. Yeah, it's the same problem with sports. I feel like, अब थोड़ा ओलंपिक्स में मेडल आना शुरू हुआ है इंडिया का ज्यादा, बट up until let's say 2000 2010, it was pathetic, like, how many medals you got. Like, why is that? It's because, again, that the depth of training and facilities and that mindset, even in sports in India, I have seen that the coaches play the role of, teachers in classrooms. Like they don't let the athletes, or at least used to be the case, 20 years ago, that they would be like कि भाई हमारा डंडा चलेगा, like for example this wrestling guy maybe still does in this wrestling
Yeah.
federation, like, they treat it as a fiefdom, and it's like my castle, I will run things. And in that kind of a scenario, uh you know people don't excel, or they don't let people excel even if they want to excel.
So जब आप नए स्टूडेंट से मिलते हो in colleges, so
Hmm.
what are the earliest sign that they are independent thinkers?
Yeah, I think, again, the signs are there. For example, I was teaching quantum mechanics, right? I can say something that the student doesn't understand. Nowadays, forget even AI tools for learning. Like you had Google, right? You can go a search कि भाई अपना माथा खुद से थोड़ा पीटो, उसको समझो, like, work on it yourself, and have the courage to be confused, to read 10 pages and still not know the answer, and then go find again another 10 pages to read and still not know the answer, and then find the clarity, right? That is what independence means. कि भाई आप जाके answer मत पूछो immediately. If you are stuck, don't go ask somebody the answer. Like if you all, I mean, because in classes, like, that is the kind of thing, right? Quantum mechanics has been known for 100 years. If as a student you get stuck, you can just go to your teacher and ask. But one should also think about it yourself, because that is how you learn. You will make mistakes, you will eventually find, and research is like that, because in research there is nobody there to tell you the answer, right? So then you have to write code, get some data, falsify your own hypothesis, do something. This is the kind of attitude which is needed. And again, that is inculcated over time, that doesn't come overnight. I think nowadays, at least, there are good institutions in India, at least at the undergraduate level. So if you are talking after 12th, right? Like ISERs are there. And ISERs, most of the faculty are more modern because these are younger institutions. So most of those faculty have had their training abroad, and they know the kind of culture that is there in the labs and departments in the West. And it has brought about a big change. For example, there are a lot of good present day physicists, like my contemporaries, let's say, who did their undergrads in ISER. And they went on to do their PhDs in really, really good places abroad. And many of them are coming back to join as faculty in India and so on, right? So ISERs have been a big kind of shining star in terms of undergraduate training and also PhD research. Like some of the very good, um, even PhD students, like ICTS gets postdocs who would have done their PhDs from ISERs. But at some level, it becomes very hard to change the mindset if you know 12th ke pehle, you don't have that. So I think one tries their best. Like at least I know many people in all these institutions, who inculcate the best practices and try to have these discussions openly. That don't say sir, don't be afraid to say your mind. Read the papers. Come to the lunch table with your ideas, even if they are wrong, etc.
So you wrote that famous page curve paper at IAS where postdocs have complete freedom, no teaching, no courses. And now you are at ICTS, you are teaching students. How does that change things?
I think that is just a different phase of life because at IAS I was a postdoc, and in the postdoc years you have very little responsibility except to do research. But postdoc doesn't stay forever. So the normal path is like, yes, you could be a professor at a place where you don't have to teach. But at ICTS, we have minimum teaching load. You only have to teach one semester out of the whole year. And there are PhD level courses which are somewhat easier to teach than undergrad level courses because you can assume more knowledge. So teaching, I don't find that very burdensome. Uh, it is true that sometimes, confronting these kind of issues about the modes of thinking or having enough hunger to pursue a problem independently. I wish one had to had less of those conversations or think less about them. Like, you wish that the students were more sort of, yeah, just more independent, more like more aggressive, going, reading things by themselves, trying things out by themselves. But, um, we get very good students. Like technically they are very good. Like because ICTS, TIFR, at least in the math and theoretical physics, they are like the best students in the country, right? So there is no problem at the level of doing an integral or solving some differential equation or writing some program. It is about the whole cohesiveness that has to come together, like that willingness to be confused, that uh, being okay with being confused, being okay with not knowing anything, and having the courage to speak up during a seminar, ask a stupid question during a seminar if you're not following. So those things kind of are automatic a bit in the US, whereas in India you have to push a bit. And the other thing is that dealing with the government bureaucracy sometimes can be a bit of a pain. So again, at ICTS and TIFR, I think have inculcated a insulation kind of from the government bureaucracy because our staff are very well trained and they are very friendly and they take care of a lot of things. But sometimes just like visa issues for foreign visitors, like when seminar speakers come to visit, how do you get their visa? Or like last year the government cut funding for postdocs, like now we cannot have as many postdocs as earlier. So things like this are, one hopes that one doesn't have to deal with and one just gets a clean slate to work with students and just think about the physics. But the nature of the job is that at some level the humans have to fix the system. So if by being a faculty at one of these places you can contribute to the system overall becoming better, that is not a bad thing. You improve the processes, you give some feedback. um, but but yeah, I think one of the things that is also holding back, you asked about experimental science, right? So there are these things you don't realize and they're often very mundane to discuss at a podcast like this, but practically speaking there is this gem portal of the government of India. So if you need to buy some equipment for your lab, the rules are that you have to first go through that portal, and that portal might have some vendor who is supplying some cheap equipment. And the fact that you have to use a government grant, you cannot go, okay, I don't know all the exact rules, but this is a big pain for some buying some things, right? Or fixing your lab with the latest, most modern, maybe more expensive equipment. And not just equipment, like the air conditioning needs to be proper because if I have a laser in my lab, the AC and the electricity system needs to work. Otherwise, the laser might stop working. Or the chilling system, the cooling system has to work properly. And quality, if you want to get quality such systems, you have to pay money, right? So these are the kind of things also which are very mundane to discuss and kind of should not be there, but they are there. So that is the thing that the government can also improve, is to streamline this kind of bureaucracy. That if I'm getting a grant, don't ask me 15 questions about why I went to this conference, book ticket from this particular website. Like, again, the people in Delhi maybe have this attitude of trying to control all kind of corruption that might happen. I'm not saying all the scientists are honest, and maybe some scientists do steal some research grants and buy an expensive ticket, later cancel it, whatever. Like, maybe there is some amount of pilferage that is happening, but that doesn't mean that you need to bottleneck the system of everything going to Delhi for approval, like every single expense that I need to make. Like, that becomes a real headache and a problem especially for experimentalists. Like, for theorists, it's nothing. It's like, I need to buy a computer, maybe I need to travel, and that's it. But for experiments, like, imagine the number of objects that are there on a complicated optics table. But every single equipment, if you have to think, oh, should I have to go through this gem portal? Is it available there? Can I spend, 1,000 rupees less or 10,000 rupees less? It is just not a very conducive environment for that cutting edge aggressive research. So that is what I mean, that, if you're spending money, be ready for a certain amount of pilferage at the expense of, efficiency. At least the people who are doing well, you need to enable them and not bog them down, with the bureaucracy.
So there is a new scheme by government, PMRC. So this scheme is for Indian researcher working abroad. So why would a permanent researcher working abroad, with a functioning lab, why would come back to
Yeah.
India?
Yeah, it's hard to kind of debate about various because this is also a policy I have not read much about. But it does seem like if it's only a 5-year project and not a full-time position, then it's very um, not very conducive to long-term benefits to Indian society.
Yeah. You
Like,
came through the permanent faculty position, not through any fellowship. So that difference
yeah,
actually
so there are some fellowships I think which are better, like this Ramanujan fellowship, which is for younger researchers, who come to basically do like a more fancier postdoc in India. But then it is geared towards people who want to stay in India and get a faculty position in India later. Because anyway, if you take a postdoc fellowship to come to India, it's very hard to kind of then, go back to Europe, just how the job market is these days. So those kind of fellowships at a younger stage are better. Or if they were, making a permanent faculty position for the senior people, giving them a higher salary, but inviting them on a full-time job, like not for like 5 years, like, or something. Um, but maybe it will be useful. That's why it's hard for me to say. Like, in theoretical physics, I don't see like much of a use for this. Um, but maybe one, to give the benefit of the doubt, like, let's imagine a situation where this LIGO India is coming up, and they need somebody with a special expertise to spend a few years to help the LIGO to be built. For maybe it's useful for those kind of purposes, like which are more short term, like to help construct a lab and then, they can go back or something like that if they have the bandwidth. But then also they have to be committed to do that for 5 years, like, because people who are permanent faculty at other places have a job at the other place, and have students and their lab there. So, yeah, I don't know. I don't want to comment on it. I have not, thought deeply about it. Yeah, it does seem that though having more lucrative, attractive positions for people to come permanently back to India is thing. And again, it's not most of the times about the salary. The salary is good. Like, we get a very good monthly salary. For example, it's about the travel grant. For example, when we hire postdocs at ICTS, they get a salary of 50,000-60,000 rupees per month. Okay, that's $600 per month. It is nothing compared to $6,000 that they would get in the US, right? It's a factor of 10 drop. But they are not worried about the salary because they know that the living expense in India is less and they will get a housing and everything is very cheap at government colleges. But air ticket will not be cheaper, right? If I have to go to a conference in Europe or if I have to go to a conference in the US, the air ticket will cost $1,500, $2,000. So, that is the question that the postdocs, international postdocs coming to ICTS ask. So there is a, so that is why, you need to give the freedom of these expenditures to the individual researchers. Give them a corpus of money, let them decide that this much I will give for travel, this much I will do, instead of trying to decide everything top down. Because the central planning, cannot be so detailed that they know about every single use case that the money is going to be spent on. So, so what I'm saying is that, money has to be spent in places where it is attractive. Like, it is not more attractive to give a higher salary in India, but it is much more attractive to give a higher travel allowance, to give a higher, to reduce the burden of bureaucracy. If you say, come to India, you are a professor there, you will have almost no bureaucracy to face. Like, and if that culture changes, I think many more people will come back, especially experimentalists, right? Because experimental physicists know how hard it is to set up a lab in India operating under these constraints of where to buy the equipment, whether it's expensive or cheap or whatever, right? And that is a real problem. So I think the government needs to think a bit and do a kind of a consultation with people that, what is really needed. Like, higher salary, in my opinion, is not a big attraction for people to come.
So yeah. So would you like to recommend some books which you have read in your career and have changed your thinking level?
Yeah, one really sort of technical book, which is also not technical, it's like a popular account of technical research, is this book Capital in the 21st Century by Piketty. I had read that book a few years ago and I found it remarkable, both in terms of just the ideas that are being presented like there and was new to me, but also the way he explained things in the book. So I think that stood out to me as a kind of a teaching of how, technical people, if they're trying to explain their research to a popular audience, should write a book. One book that I read, I mean, it was a long time ago, but thing that obviously had a big impact on me was this book India After Gandhi by Ramchandra Guha. So that explained, post independence politics and put things in context. So that is like one book that has stayed with me. The other is this Capital in the 21st Century. I mean, there are these standard Feynman books, but I think for me, they have not aged very well as I have grown older and look back at them. I mean, I read a few biographies. The biography of Paul Dirac was actually the quite interesting to read. Uh, there was the biography of Paul Dirac that had come out recently. I read a biography of Pauli as well and von Neumann, but those particular ones that I read were not that interesting. But the Dirac one was interesting. And the interesting fact about that is that even though Dirac was one of the inventors of QED, like he wrote down the first kind of, he went to his grave not liking renormalization. He thought that renormalization of all these like subtracting out these infinities and stuff is a bit of a cheating. And he always wanted to, have a better theory of QED, like something where you wouldn't have to do this subtraction of infinities. It was kind of amusing that somebody who kind of invented the subject then became very aloof from how it developed later, in QED especially.
So your current research work is focused on low dimensional of quantum gravity and black hole.
Yeah,
So I often hear about lower dimensional model of quantum gravity because they are mathematical tractable. But why
yeah.
do physicists simplify by going to fewer dimensions rather than more dimensions?
Well, fewer dimensions is simpler, that's why, right? Like higher dimensions is more complicated because there is fewer things that can happen in lower dimensions. So just because there is less space, like you are in low dimension, there is less space. So there is less moving parts to the problem.
So to understand quantum gravity, you need to go to 2D models rather than 5D or 10D models.
Exactly. So the 2D models are simpler. Well, sometimes you kind of throw the baby out with the bathwater. So that happens that, for example, in 2 dimensions, even the electromagnetic field, there are no photons in 2 dimensions. There's purely just Coulomb field. Same thing for gravity. Like there are no gravitons even in 3 dimensions. But there are features of the higher dimensional problem that remain. So what happens in toy models is that, your original problem is very complicated. It has 5 or 6 moving parts. And you want to understand all of them. And sometimes understanding them is kind of an independent task. So what happens when you go to lower dimensions is that maybe 3 of those 6 features will not be there. So it allows you to understand the mathematical nuances of the remaining 3 things, in a kind of isolate them and study them separately. And then you can take your knowledge and apply it back in the higher dimensional problem. But one should always try to go back to the higher dimensional problem.